Hello, and welcome to the lecture for Chapter 16 of Astronomy Today on the topic of the Sun. This is a very neat lecture because all of our previous lectures have talked about the rest of the solar system, the planets, the comets, the asteroids, the dwarf planets in the Kuiper Belt, the other Kuiper Belt objects, the comets in the Oort cloud, but all of that is a tiny fraction of the solar system. Mass-wise, less than 1%, and the Sun makes up everything else. This is what the solar system is all about. This is where the dramatic physics takes place. This is what sustains life, and it has an unbelievable amount of power. Okay, so let's talk about the sun. We'll talk about its physical properties. All right, that's kind of a general overview like we have done with the planets. We then will talk about its interior, which makes sense. It has layers, again, analogous to planets. We'll talk about some of those details of the layers because they certainly have some very different characteristics than from terrestrial planets or even gas giants. All right, some really unique properties that only stars have. Then we'll talk briefly in this little discovery note about eavesdropping on the sun. Just a couple of very interesting missions and space probes, their location, and how they can get such relevant data of the sun. Then we'll get into the sun's atmosphere. All right, there's a very well-defined atmosphere. It's actually easier to study than the interior. That probably shouldn't be a surprise. There's some layers to that atmosphere, but there's also some very interesting characteristics about it that are incredibly unique, that interact with the rest of the solar system, and just are dramatic in their high temperatures and so on. And so we'll certainly talk about that. One very important idea when we do talk about the atmosphere, stress it now, is the corona, both because it is so inexplicable in some respects and because it's so dramatic and unlike something that we would see anywhere else in the solar system. We will then talk about the solar magnetosphere and magnetism in general, a lot of magnetic effects of what's happening with the sun. We'll talk about the active sun, and this really highlights this idea that the sun is unbelievably powerful, almost scary, chaotic, releasing huge amounts of energy, and in a number of interesting ways, many of which are driven by the interactions between light and charged particles and magnetism. So electromagnetism in general, because we have electric fields, we have magnetic fields, we have charged particles that are interacting with the magnetic fields. And then, of course, that's all tied in with light because light itself is an electromagnetic phenomenon that's made by a accelerating charge. So it's all these ideas are tied together. We then will briefly touch on this idea, which is kind of begging to be answered, is how much does this active sun affect Earth? And the cycles that the sun displays and undergoes and all the energy that's released. And there's definitely effects on Earth, both ones that can be expected and unexpected. Then we'll get into something that is truly unique to the sun, and that is its heart. All right, that is where fusion takes place. All right, nowhere else in the solar system is there fusion acting. Okay, now to be fair, humans have started fusion not in an energetically favorable way. We can create fusion in a lab. We can fuse light particles together as the sun does, but we can't do it to generate energy. We end up spending more energy containing the fusion than actually the fusion produces. So it's more of a proof of concept. We can't recreate the power plant aspect of the sun and its ability to create energy through fusion of matter. All right, so this is unique to the sun, and this is special, something we would not do with the planets, because when we talked about the interior, we were done, and we said maybe there was a magnetic field that was created by that interior, and there was certain densities inside the interior, a molten core in the case of terrestrial planets, but no. For the sun, there's a heart and something truly unique happening there. Okay, we'll then talk a little bit about the physics of that truly unique process, fusion, in terms of the fundamental forces, and then the proton-proton chain, which is the particular type of fusion that a star like our sun undergoes, because there is different types of fusion that have been theorized and the data from other stars have backed up. They're similar, but there are some important differences. Our particular star, our sun, has a proton-proton chain. Okay, and then we'll get into one last little topic, which is the solar neutrinos. Because throughout this discussion, you might wonder, how do we know this? How do we know this information? How do we know? We're not sending probes inside of the sun. the few probes we have are orbiting the sun, all right? This much like Earth orbits the sun. So how do we know so much about its interior? How do we know so much about the fusion that goes on? Well, it's all based on models, and those models need to be backed up by some observation. We'll talk about that in terms of seismic waves in the sun and the actual features on the surface of the sun and the atmosphere of the sun. So those are direct observations. But neutrinos, interestingly, are one of the only things that directly tells us about the interior, because neutrinos are tiny little particles that actually come from the heart. All right, they come from the heart of the sun. They come directly from the heart of the sun, traveling at nearly the speed of light, and then we can observe them here on Earth. You might be thinking, well, doesn't light come directly from the heart of the sun, and can't we observe it here on Earth? And the answer is no, it's not direct. The light that is created inside of the sun and would tell us something about maybe what's happening inside the sun, well, that light takes millions of years to reach the photosphere, the part of the sun we can see. Okay? So neutrinos are our window into the core, our window into the heart of the sun. And that will wrap everything up, so let's get to it. Okay? So starting with some important details about the physical properties of the sun. Okay? So it's got a radius of about 700,000 kilometers. Compare that to Earth's radius, which has a value of about 6,300 kilometers. Okay, so you see that size difference, right? Almost 100 times the radius, right? So the sun is almost 100 times bigger across. That's a huge difference, especially when you consider volume. If something has one side that's 100 times longer, and then you consider, well, that's length, and we got width, and we have depth. So then you have a factor of 100 cubed, and 100 cubed is a million. All right, a million. And I bring that up because that's kind of a rough estimate. We can say the sun, since it has a radius about 100 times bigger, that means that its volume is about a million times greater than Earth's. So good rule of thumb there. The sun is about a million times the volume of Earth, okay? And it ends up being a lot more than a million times the mass, and that's because it's made out of denser stuff, especially its dense core, okay? So here is its mass, right? It has a value of 10 to the 30, okay? So that's, again, dramatically different from the mass of Earth. Close to a million, actually. I know I said it was a bit more, but it's close to about a million because Earth's on the scale of 10 to the 24. But then we get into its density, and we see that it is denser. All right, its average density doesn't exceed Earth's by too much. It ends up being about 1.4 times denser than water. And actually, to be fair, it actually is slightly less dense than Earth. I didn't misspeak there. This is more comparable to a dense gas giant. All right, so it's about 1.4 times the density of water. All right, and I guess it has a very dense core, but it is important to consider that its outer layers are not all that dense. They are gaseous, very hot gas, but still gaseous, and that does bring the density down. So less dense than a terrestrial planet, obviously much larger. I mean, a million times larger, but less dense than a terrestrial planet, which is all the heavy leftover stuff like Earth and Mars and certainly Mercury, right? Just heavy leftover rocks and minerals in the terrestrial planets, but denser than most gas giants, right? So we consider here that like Venus, for example, has a density that's less than 1,000 kilograms per cubic meter. So we have maybe over 1.5 times denser than Venus, okay, for the sun. Now, one thing, if we're making comparisons to gas giants, it's important to consider its rotation because it's differential. All right. Now the period is about a month on average. Okay, that's how long it takes the surface to go around, right? So if we're looking down on the sun, the time it takes that one point on the surface to go all the way around is about a month. But that varies dramatically between the poles or points near the poles, because the poles themselves are not rotating. But certainly between the near the poles, high latitudes, and the equator. And that's because the sun is very much a fluid. It's a swirling sphere of fluid held together by gravitational forces. And its fluid properties are more front and center, more dramatically displayed than the fluid properties of the gas giants. Certainly there is differential rotation. We talked about it for Jupiter, for Venus as well. It applies to all the gas giants, but less so to Uranus and Neptune. But for the sun, it's quite noticeable. You have the equator, the equatorial sections are spinning faster, and so then there's shearing between the layers of the fluid that makes up the sun as it spins around. Okay. And what we see, so that's the apparent, what we actually see of the sun is its photosphere. So if you look at the sun, don't want to look directly at it, but when you glance at the sun, then that is the photosphere that you're seeing. And we'll see that term because that's part of the atmosphere. That's the lower atmosphere. Okay, but the visible part is the photosphere. We don't see the other parts of the atmosphere because they're not bright enough. So they're washed out by the color of the photosphere. Simply that. Okay? All right. So there's the physical properties. Here is an image of the sun, this filtered image of the sun showing sunspots. All right, we'll talk quite a bit more about those. The sharp edge of the sun, that's the sharp edge of the photosphere right there. And then due to the thin photosphere and the corona. All right, so the corona is this extension here that you would not see because it would be washed out by the light of the photosphere, but you can see under certain circumstances, such as in a filtered image, or we'll talk about the other common way you can see the corona. All right, well, maybe not common, but a way that everybody can see the corona given the opportunity. Okay, but we'll get to that later. More about physical properties. All right, well, there is structure to it, right? We got layers of the sun as we're used to seeing layers of any planet. All right, so that definitely holds true. All right, the outer layers are not to scale. Okay, we've condensed things down a bit, so the corona would be larger. Okay, and the core is where the fusion takes place. Okay, the core is the heart, the term that we used in the table of contents for the lecture. Okay, so there's the core. I'll zoom in this a bit. We can see that huge size, going all the way up to our 700,000 kilometers to get all the way to the top. There's some other information here, all right, including the actual thicknesses. Okay, and that's since they aren't shown to scale, these ones, in addition to the corona, so the scale comment is also applicable right here, because you can see the photosphere is only 500 kilometers, right? And 500 kilometers would not show up on a picture that is trying to capture 600,000 kilometers in terms of the overall radius here. So it would be a tiny, tiny layer, like a super thin crust, is actually what the photosphere makes. Not to say that it's made out of solid material, but it really is really dramatically thin. All right, but we've shown it more clearly here. Underneath the photosphere is the chromosphere, okay, and the transition zone, which is where we go from convection to the very surface. All right, these are zones we will not talk about too much, but what we certainly will discuss in just a moment is the convection zone, what's going on there, and the radiation zone, and why those are unique and important layers of the sun. Okay. And we will come back to the corona. We will talk about the solar wind as well when we talk about variations in the corona. Okay, so moving on, we have some values here which are really important when we remember that the sun is a huge source of energy. It is the energy that supplies the rest of the solar system. I mean, to be fair, if we look at the gas giants, they are obviously outputting more energy than they absorb from the sun because they are in themselves sources of energy, but not on the same scale. They don't light up the sky like the sun does for a terrestrial planet like Earth. So we have a huge amount of energy that comes out. That energy is represented as luminosity. Okay, so luminosity is wattage per square meter. Okay, well, actually, that's intensity. Excuse me. So luminosity is just wattage. Let's make that clear. All right. So wattage, watts. All right. That is what we mean by luminosity. So because what are watts? Well, watts are energy per time, and that's if we're just talking about what the sun produces, that is energy per time. Okay, and if we wanted to say, how much total energy over a million years, then we just multiply by however much time there is in a million years. This is traditionally going to be in joules per second, joules being the unit of energy. Okay, so the total energy radiated by the sun, and it can be calculated from the fraction of that energy that reaches Earth. Okay, because there's no way for us to build a big net around the sun and actually absolutely confirm experimentally that this is the energy. Instead, we think about how much energy hits a small point on the Earth, calculate the overall energy that, the overall chunk that represents of the sphere of energy that's spreading out. And then from there, we can then estimate the total energy output of the sun. Okay, and it can be a pretty good estimate because we can take multiple data sets and really compare between them to get reliability. I'll show a picture of that in just a moment. Okay, so the solar constant has to refer to a planet's perspective on that energy, and it's the amount of sun's energy that reaches Earth. Okay, so that's the average amount of energy, and so here we do have an intensity. So the solar constant is often also represented by the word intensity. That's the name of the unit, and the intensity is watts, which is joule, energy per time, but it's going to be watts, which is power, all right? That's watts are our unit of power. Luminosity is another term for power, but in intensity is watts per area, okay? Or watts per square meter. So power per area, okay? We can write it that way, power per area, all right? That's what intensity is, and solar constant is just another name for intensity. And different planets have different solar constants because you calculate it by knowing how far the planet is away. And it falls off as the square of distance, as we can see with the meter, because as you get further and further away, there's less and less of a solar constant, there's less and less intensity of light. But it doesn't just decrease gradually, it decreases rather dramatically because of that square of distance. And that's because it's covering a sphere, all right? The energy has to be spread out over a larger and larger sphere. And then finally, total luminosity ends up being, once you actually calculate it, 4 times 10 to the 26 watts. That's a huge amount of energy. It's the equivalent of about 10 billion 1 megaton nuclear bombs per second. Right? So it's just an unbelievable amount of energy that is released from the sun every single second. It's an unbelievable amount of energy when we think about the fusion as well, because this energy actually comes from turning matter into energy, mostly kinetic energy of the products of the fused particles, but as well as just pure photon light energy. But point being is that is actually a huge amount of mass that's being converted, just mass disappearing forever, becoming energy. Because that's what suns do. They eventually run out of that fuel, but it takes them billions of years. But we're getting ahead of ourselves. We'll talk about fusion in a moment, okay? But that's the actual power output. Power output, okay? Biggest numbers in the solar system right here. Okay, so I kept mentioning this idea of the energy covering out or covering a sphere. So that's the idea, because the energy that's produced by the sun spreads out in all directions. So you can think of it as a spreading wave, a spherical wave of energy. And so then if you look at Earth, Earth not shown to scale here would then be just one small point on that overall sphere of energy. And then if we had a measurement like a big solar panel or something somewhere on the surface of Earth, and we're measuring exactly with that solar panel and careful device measurements, we can then say, okay, well then we have this small amount of area. That small amount of area is a fraction of the overall sphere, and then that's how we calculate the total luminosity. Okay, that's how we get the entire output of the sun. Okay, and it definitely shows here, as we see that energy spreading out, that if you're on a planet like Mars that's further away, well, that's going to be a bigger sphere. So it's the same amount of energy because the sun's still producing the same amount of energy, but Mars being further away, that energy is more spread out. Thus, Mars perceives less of the energy per square area. So if they built a similar solar panel on their surface, it would not produce as much electricity. Okay, all right. So let's talk about the interior. Now we'll come back to the interior when we talk about the core where the fusion happens, the heart. But let's do some typical stuff like we do for celestial bodies, planets included, and just talk about the ideas about the interior. So we have models of the interior, again, because we don't go there ourselves, and they are consistent with observations, okay? All right, those are gonna be observations of the surface, observations of those neutrinos I talked about, okay? So the idea is that the sun is an equilibrium, all right? There is a inward force, which is gravity, represented here as blue, that wants to crush the sun. The sun is dense enough and the gas can't really withstand that. It wants to crush under the force of gravity. It wants to become denser, okay? However, there is an outward pressure. That outward pressure is because of the fusion that's occurring in the core. The outward pressure is all generated from the core, and that pressure then is transmitted throughout the entire bulk of the sun, but it starts at the core because there is energy released in the core. That energy then is transmitted to the kinetic energy of things like helium, all right, ionized helium, but helium nevertheless, and that helium then bounces around, but bounces into other helium particles, and that means that they push outwards. Okay, just like when you heat up a gas, the gas is represented by a bunch of particles bouncing into each other and they push outwards, like a balloon heating up in the sun and expanding. Okay, expanding till it pops because there's nothing to stop the balloon besides the elasticity that holds the sides of the balloon together. But in the case of the sun doesn't just expand till it pops because gravity holds it together. All right, so it's a balancing act. Gravity pushing it in, the fusion and all the energy from the core wanting to blow it up. Okay, now we get observations, that direct data of the sun, by looking at its surface. That's one important way. All right, and we can see when we look at its surface, we can see that its surface is made up of convection cells. All right, that we measure through Doppler shifts because there's all this light coming from the surface of the sun. If that source of light is moving towards us, it gets blue shifted. It's all right. That's a part where it's bubbling up towards us. Okay, we'll talk about how the surface of the sun is like a bubbling mass, almost of lava or something. And so if the surface is coming towards us, it's blue shifted. If it's sinking away, it's red shifted. Right, and that's the Doppler shift idea. All right, and that's important because we can really measure that carefully and see how those surface features, how that bubbling surface of the sun matches the amount of energy we would expect, and so on. And there's one other important thing we can do with the sun, and this is the way we study the interiors of planets as well. We do it directly here on Earth by measuring seismic waves. And here we can look at light waves that are behaving as almost like seismic waves, like sound waves, that travel through the sun and behave differently in the different parts. All right, so they actually, we can look at the refraction of those waves as they travel through the entire body of the sun. Okay? All right, so here we're going to now discuss its density, because we saw its average density was of the sun, of course, was 1,400 kilograms per cubic meter. All right, that's its average density. But it varies quite a bit because the core is much, much denser than the rest. All right, so we want to talk about that and how that variation in density and temperature matches up with the model we have of the sun. So far, the model is just based on those observations of the surface that I was just talking about. Okay, but here is another picture of our onion layers of the sun, right? Not exactly shown to scale. But let's take a look then if we're going to measure across the sun, so from that point to that point, and we consider two different graphs, one with a measurement of density varying across that line, all right, with distance from the center of the core. We see that the density measured in thousands of kilograms per cubic meter goes way up in the core. Right, so we end up with 160 times 10 to the 3 kilograms per cubic meter, all right? Well, that's 160,000, all right? 160,000 kilograms per cubic meter. Now, the density down here is really, really low. Look, the density in much of the convection zone is so much lower because it's right down to about 1, right? So look at the scale, right? Because 1 is about water, 1,000 kilograms per cubic meter, or just 1 times 10 to the 3, all right? And so that's that very low density, that makes up much of the sun. But the core is so dramatically different. It is so dense, and it is so much denser than even terrestrial planets. It's so much denser than just about anything. There's no elements, even the most dense titanium or uranium, gold, very dense elements. None of those would come close to being 160,000 kilograms per cubic meter. All right, so the sheer density of cores of stars like our sun is a really dramatic number in astronomy. It's a striking number. The only densities that exist that are greater than this in the entire universe are the dead cusps, the dead cores of giant stars, which are things like neutrino stars and even white dwarfs, which our own sun is hypothesized to become a white dwarf eventually. Those are even denser than the current core. All right, white dwarf more comparable, neutrino star noticeably denser. But point being is that it's incredible that the core is like this, and it's because it's so packed down from gravity. Gravity has condensed the core so much and made it so dense that then and that equilibrium is applying to the core, and that energy is being released because that density has led to, you might have guessed it, a high temperature. Because of high density, you get high temperature. With high temperature, if it's high enough, you get fusion, the energy source of the sun that produces all that incredible numbers we saw in terms of its overall luminosity. It all comes from high density leading to high temperature. Because look at these values. This is in millions of Kelvin. So when we get to the core, we have about 16 times 10 to the 6, because 10 to the 6 being a million, Kelvin. Okay? That is incredibly hot. The value for fusion is about 10 million, so 10 times 10 to the 6 Kelvin. To compare that to everyday room temperature is about 200. Well, actually, it's about 300 Kelvin. Right, 273 is like freezing. That's like 0 Celsius. But 300 Kelvin is about room temperature. Room temp. So you kind of compare that. You're like, oh wow, that's quite a difference. And then you consider the temperature to melt something, like to melt metals. That's going to be in the range of thousands of Kelvin. Sometimes it's 100, maybe 900 Kelvin. but you can get up into 1300, 1600, even 6000 Kelvin to melt the densest metals. Well, that's fine. Okay, we're getting up into thousands. What about tens of thousands of Kelvin? Well, that's more than enough to melt anything. But now we're into tens of millions of Kelvin is the core of the sun. So there's a huge temperature difference there. The typical human activities are going to be only up into the thousands or tens of thousands of Kelvin. And so, but then the sun maintains tens of millions of Kelvin, which is why it's so hard to sustain fusion here on Earth, because we can't sustain those high temperatures. Those high temperatures require a lot of pressure, okay? But that's what the sun does, and that's what actually allows for that unique physical process that is fusion, fusion creating energy from matter, okay? All right, so good. There's the solar interior and some very interesting graphs. And now I think we're well placed to talk about some of the interesting aspects of the solar interior. And one good way to talk about that is to think about the energy, because we keep coming back to this idea that this is the power plant of the solar system, the sun, and it's producing energy. The energy starts in the core, makes its way out, which is its transport. Okay, so after the energy is created in the core, all right, well, then there's the radiation zone, which is quite interesting because it's relatively transparent. Okay, now the radiation zone is still quite hot. We saw that here. The temperatures in the radiation zone are still going to be in the millions of Kelvin, or at least the hundreds of thousands of Kelvin. So how is that if it's transparent? Because transparent means that whatever photons are coming out of the core are passing right through the radiation zone without transmitting any of their energy. So the photons are going through the radiation zone without being hampered by it, which means they're not leaving any of their energy behind. Well, it means it's kind of behaving like glass almost. Now, of course, it's a much higher higher density exotic version of glass, but the analogy is there. It kind of behaves like glass. Because you think about glass is transparent to sunlight. So if you leave glass in the sun, it doesn't really heat up. But if the glass is sitting on something, that like a black table, for example, well, that black table does heat up in the sun, and then the glass will become warm because it's resting on the black table, because the glass still can become warm through conduction. It's just not getting warm through radiation. And that's what's happening with the radiation zone of the sun. Still warm because it's conducting energy through direct physical contact with the core, but not getting any energy through the light that it's allowing just to pass right through it. Okay? All right. Okay, now, and it does it even, and it's not even perfectly transparent either. Neither is glass for that matter. Okay, but then what happens is then that energy, the photons that were able to just pass through the radiation zone, they get to the convection zone. Okay, and the convection zone is not transparent; it's the opposite. It's opaque. All right, and because it's just like a dark material. And so all the photons come to a stop in the convection zone. They transmit all of their energy to the plasma, which is just the ionized, very hot gas that the convection zone is made out of. And to be fair, so is the radiation zone, but a plasma in a different state. But regardless, once the photons get to the convection zone, they transmit all their energy because they get absorbed by the opaque convection zone. And where does that energy go? Well, it goes into actual convection of fluids. Convection is just the bulk movement of fluids. So all that energy that was bound up in the photons now gets absorbed by atoms within the convection zone. They start moving around, but since it's so dense, they're not moving like a gas, so they're just randomly bouncing around. Instead, you have hot plumes of fluid rising up, cooler ones sinking, much like convection occurs in the mantle of Earth. Okay, all right. Okay, and then obviously this process is the overall energy transport, and I mentioned that it takes a long time. The transport takes about 1,000,000 Earth years. And what I mean by that is if you think of the one photon being created in the core, well, then that photon then has to travel out through the zone, the radiation zone that is, get to the convection zone, and then that energy has to rise up to the surface. Then it produces a new photon that comes to us. Well, then the photon that's produced on the surface of the photosphere, that photon is produced 1,000,000 years after the original photon that was released in the core that then started traveling up to the radiation zone. Just because it's such a dense object and it's so large, it just takes that long for the energy to come out to the surface. So it's quite a time delay. All right, if the core suddenly stopped working, we wouldn't know for hundreds of thousands of Earth years. Okay? Okay? Except for neutrinos. Neutrinos would tell us, but we'll talk about that later. Okay? So, continuing with the interior, we want to talk about the visible top layer, right? So the very edge of the interior. All right, and that's the visible top layer of the convection zone is granulated. So it looks like lots of grains, all right? And because it has areas of upwelling and surrounding areas of sinking. And we saw that with the Doppler effect and the blue and the red, those were upwelling and sinking sections. But here we're looking at an even tighter scale, at a more detailed scale, with a very nice actual photo of the sun in the visible spectrum. And here you can really see this granulation, these rims of cooler sinking material, and then the brighter sections of hot material that's upwelling. And that's due to these convection cells, okay, that are circling like this. See how they're circling in opposite directions? And that's the idea. That's what's happening. There's all this bubbling, swelling, super hot plasma gas, okay, on the surface of the sun at the very top of the convection zone. Okay, so how do we know about the sun, including the magnetic effects that we're about to talk about? Well, there's a couple of very neat probes out there that allow us to eavesdrop on the sun. Those are SOHO and SDO. So SOHO stands for the Solar and Heliospheric Observatory. It orbits at Earth's L1, which is the Lagrange point. And these are points where you can put a satellite and it will stay at a fixed location relative to both bodies that allow for the Lagrange point. In this case, the bodies of the sun and Earth, because there's a gravitational balance between the pull from Earth and the pull from the sun, that is. And that means that it must be much closer to Earth, because Earth is sure a lot smaller than the sun, right? About 1,000,000 times smaller. And it is. So Lagrange points are always much closer to the smaller body. There are Lagrange points between Earth and the moon that are close to the moon. You put a satellite there and it just sits there relative to both bodies, the Earth and the moon. So same idea here. That's great for being able to transmit to this satellite and so on, and get continuous data. There's another really other neat probe, the SDO, which is the Solar Dynamics Observatory. It's not a Lagrange point, but instead is at a geosynchronous point. So that means that sometimes it's out of range of Earth because it'll be on the other side of the sun from Earth. But other times when it comes back around, well, it transmits data back to Earth. But what is so neat about it being geosynchronous, or really solar synchronous, but geo just referring to the ground of the sun, is that it's always looking at the same face of the sun. And so that means that for actual data processing and filtering, there's always that same image of the sun. It means that there's kind of a far side of the sun that the SDO never sees, but one side it can analyze in great detail, and then continue to get lots of data. And honestly, you can have more than one SDO. You could have multiple SDOs looking at different sides of the sun in separate geosynchronous orbits. Okay. I don't know if there's plans to have more than one. And each carries multiple instruments measuring the magnetic field, the corona, the upper atmosphere, vibrations on the surface, ultraviolet emissions. So there's just huge amounts of data being collected by these important satellites put at very ingenious locations of Lagrange points and synchronous locations. Okay. Now, when we analyze that atmosphere, we see lots and lots of elements in it. And we only see them in particular parts because we can only see the elements that are being absorbed by the light that comes off the photosphere. So spectral analysis, that's looking at the light that comes from the sun, can tell us what elements are present, okay, excellent, but only in the chromosphere and the photosphere of the sun. Because the light is coming from the photosphere. Everything underneath the photosphere we don't see because it's beneath the source of the light, which is the photosphere, where the photons are being recreated after the convection zone. All right, because they were absorbed in the convection zone, and the energy was transmitted through convection, and then photons were released again to be radiated out into space, because you can't convect through space. The only way to transmit energy through space is through radiation, which is photons. But regardless, we got this idea that we have the photosphere, we can't see anything behind it, but we can see things above it, such as the chromosphere, because the chromosphere is above the photosphere. And so certain elements exist in the chromosphere, they absorb the light, and then we know that element is there. And we see 67 different elements, okay? So we see elements like calcium, iron, we see mercury, we see, so calcium, we see sodium, right? So lots and lots of elements, including some rather interesting elements to find in the atmosphere. We don't find a lot of calcium in Earth's atmosphere. And this is due to the fact that the sun has, even though it's not associated with heavy elements, it's mostly hydrogen and helium, there are a mix of heavy elements, and they're all getting mixed around, and some of them kind of get pushed up into the atmosphere as in an ionized state. Okay? All right. And the spectral lines are formed when the light in the chromosphere or the upper layers of the photosphere are absorbed before escaping the sun. This happens when the energy is close to an atomic transition, when there's a particular photon wavelength that matches an atomic transmission, and there's bound to be because there's a wide range of different colored photons, different wavelength photons that are created on the surface, and they then get absorbed. We can then tell that they got absorbed because of the black line in the otherwise continuous spectrum, the rainbow spectrum of the sun, because it does produce the full range of visible light, the visible rainbow, okay? The visible rainbow because we evolved to see that particular light because that's the light that exists here on Earth, okay? So that is the idea of looking at the atmosphere and the elements in the atmosphere of the sun, okay? Now, other neat things about the atmosphere is, as I said before, we see that stark line, that sudden contrast of what is the photosphere. We don't see the chromosphere, we don't see the corona, except sometimes we can, all right? So the cooler chromosphere above the photosphere is difficult to see directly, all right? All right, because the photosphere is much too bright, it washes it out, unless the moon covers the photosphere during an eclipse, all right? Now, this, in order for that to happen, so that for the moon to cover the photosphere but not the chromosphere, that requires a particular type of eclipse called an annular eclipse. Annular eclipse. Because it needs to be a case where the moon is further from Earth, because the moon has a slightly elliptical orbit. So sometimes the moon is further from Earth. And when that coincides with an eclipse, then you're going to have a time where the actual angular size of the moon is smaller than the angular size of the sun. It's always a little bit smaller, but it'll be more dramatically smaller, leaving a visible chromosphere. Right? And so that we can actually see the chromosphere, including a solar prominence right there, right? We can see some more solar prominences over there. Okay, so that's a rare opportunity for someone just, with a basic telescope to actually observe the chromosphere. But most of the time during solar eclipses, the moon is a bit larger because it's closer to Earth and taking up more angular size. And in those cases, we just see the corona. Okay, so let's talk more about the atmosphere. So small solar storms in the chromosphere emit spicules, okay? These are just little bursts of gas, all right? And we're going to work up the more dramatic things that the active sun does. But this is one thing that we regularly see in the sun's atmosphere, in the chromosphere. And we'd see it, through sophisticated telescopes because we can see those year round, or in the rare event where a basic telescope can do it, which of course is an eclipse, okay? And here's a more typical eclipse that shows the solar corona, because the moon is larger here, blocking out the photosphere. Right, so now the photosphere is blocked, so both the photosphere and the chromosphere is blocked, and we're just seeing the corona. And you can see the corona is much larger in size compared to the photosphere. It was relatively tight around the sun. The corona stretches out quite a bit more larger. Right, it varies in size dramatically, and so that you can have a solar eclipse where it matches up, and you can see much larger like shapes of the corona, or sometimes it has a more kind of symmetric shape like we see here. All right, now weird thing about the corona, really an ongoing mystery, although there's some good theories about it, is it's much hotter than the layers below, which means there's got to be a heat source, which is probably electromagnetic interactions. There's probably some basically energy that was still trapped in electromagnetic fields, and then that energy is allowed to dissipate and become radiation energy in the photosphere. It's almost a mechanical vibration that's allowing for more EM waves to be generated in the corona. But it's quite fascinating because it's just there's no intuitive model that suggests why the corona should be so much hotter than the zones below, like the chromosphere. As we see, the temperature of the chromosphere is about 4,500 Kelvin, all right? And the photosphere beneath the chromosphere is about 3,600 Kelvin. That would be the photosphere. And that temperature corresponds to a particular peak wavelength of the sun, which is kind of a blue-green-yellow color, but a more green-yellow color, which is greenish yellow, which is right in the middle of the visible spectrum, and that explains the rainbow, because it's the light on either side of that is the slightly less probable light that reaches Earth. But regardless, once we get to the chromosphere, it warms up, and then it just really strikingly warms up until we have these incredibly high temperatures, almost 1,000,000 Kelvin in the chromosphere. If you remember, I was talking about how dramatic 10 million Kelvin is in the core of the sun, because 10 million Kelvin is hot enough to sustain fusion. Well, 10 million Kelvin being a dramatic number, so is 1 million Kelvin. How is the corona so hot if it's the upper atmosphere? Shouldn't it be cold? Well, it doesn't hold a lot of heat because it's very, very low density. Very, very low density. So that, so that idea of having an upper atmosphere that has a high temperature but low heat, well, we see that with the planets, right? We see that with Earth, right? Earth's upper atmosphere is actually way hotter than the life-sustaining lower atmosphere that we're living in and breathing in right now. And so why is that? Well, that's because X-rays that are produced from the sun get absorbed in Earth's upper atmosphere, and they then transmit to the few particles that are up there, giving them a very high average kinetic energy, which is what temperature is related to. Temperature is directly proportional to the average kinetic energy of the particles that the temperature refers to. And so you have a lot of energy per particle in Earth's upper atmosphere, so it has a high temperature. But it doesn't have high heat, it has low heat because there's very few of those particles. There's incredibly low density. So you'd still freeze there, even though the individual particles are very fast, this high temperature. So same idea with the corona. The corona has a high temperature, but low heat. But regardless, that's a really high temperature. That's nowhere close to the relatively high temperatures of the upper atmosphere of a planet like Earth. And also the fact that Earth's upper atmosphere is hot can be explained by the existence of X-rays that are created by the sun. But is that what's happening here? Or is the sun absorbing its own X-rays? Well, that doesn't seem likely, because if the sun is absorbing its own X-rays and that's what's heating up the corona, then there wouldn't be any X-rays left over, or not enough to be left over to be absorbed by the planets that we directly see evidence of. So then how is the corona getting so hot? And that's the question that scientists continue to ask. And again, there's some good theories and hypotheses, but not a conclusive answer about why the corona is so hot. So neat area of active research. Okay, so going back down to the surface of the sun, we're going to talk about a lot of effects of electromagnetism, solar magnetism. Okay, so we'll start with sunspots. Those well-known imperfections. They've been known since the 1500s. Galileo was the first person to discover them. All right, so we've got lots of sunspots. They always appear dark. Okay, so when they're shown that way, that's accurate in the visible spectrum. They are dark, but that's because they're cooler. They're cooler than their surroundings, right? And they're not cooler in the sense of the sinking fluid in the convection zones. They're cooler in a separate way. So the sunspots are not part of the convection process. They're more like interruptions in the convection process. Okay, but they're not. They also don't cover the entire surface. The entire surface was granulated with convection. The sunspots are much more sporadically covering the surface, and they go through a cycle, which we'll talk about. Okay, and the sunspot has a very dark center known as the umbra, and a less dark center around called the penumbra. Terms that are the same for shadows. Okay, so they come and go, right? They last a few days. So an individual sunspot will be around for a couple days before it just fades away. Okay, so why is that? Well, that's because they are linked by pairs of magnetic field lines. So there is a magnetic field line at the surface of the sun, at the top of the convection zone, right where the photosphere is, that shoots up a south magnet. So it's almost like a big bar magnet has floated up to the surface, and south end is pointing up. Nearby, there's another north magnetic pole, and then since those two magnetic poles are close to each other, they connect, field lines connect, charged particles travel along those connecting field lines, spiraling along them, carrying with them energy, cooling the surface where the field lines began. Okay, so that's the process. Also cooling the surface, because since the charged particles are locked in spirals, they're no longer able to convect, and so they just gradually cool in the areas where the particles are trapped in those helical paths along the magnetic field lines. All right, going from, say, south to north. Okay, all right, so that's the idea. Now you might be wondering, why are there these sudden magnetic poles just popping up on the surface and lasting for a few days? Well, it has to do with the differential rotation and the fact that this is a fluid that's full of charged particles that's creating a chaotic magnetic field. Because if there's one thing you can conclusively say about the sun, is it has a very complex chaotic magnetic field, unlike the stable magnetic field of something like Jupiter. Very unlike that. Okay. All right. Jupiter's gets varied a bit, but not nearly as much as the sun, and certainly less stable than Earth. Earth has a very stable magnetic field. Okay? So the sunspots originate when the magnetic field of the sun are distorted by the sun's, differential rotation. The fact that it's spinning faster along the equator, right? So that then, so it ends up the material near the poles can't keep up with that fast moving material on the equator. And then so there's all this mixing up of magnetic field lines, right? And so then we can get these sunspot pairs, all right? And those loops then become solar prominences when they're seen on the edge, like when the chromosphere becomes visible during an annular solar eclipse, okay? And there's a cycle of where the sunspots are and how many there are. And that cycle takes 11 years, the 11-year sunspot cycle, which is so interesting. It just happens to kind of match up with 11 Earth years. Not exactly, but within a small fraction of 11 Earth years. All right, and that's a period, a cycle where the sunspot number rises, falls back again, and then starts rising again. So it goes up and down, right, like a wave. Lots of sunspots, less sunspots, and we see that here. If you look, number of years, this is about 11 years going here. All right, and we can see that there's like no sunspots at first at the beginning of the cycle. Then a few sunspots start popping up at the high latitudes, so near the poles. Then there starts being lots more sunspots, with more and more of them occurring closer and closer to the equator. So peaking in number of sunspots that basically cover the entire sun about halfway through the cycle. Then the number starts to reduce until only a few are left, and those few left are around the equator. And then we start over with there being none again, and then some popping up on the poles again, or near the poles. And this is you can see it's not perfect, and there's kind of variation, but that's the overall trend. Okay, and so the peak number, peaking halfway through that cycle, right where I drew the box here, that's going to peak out every 11 years. Right, and that's what we're seeing here, with some variation. Not every peak number of sunspots is the same, but there's a regular peak every 11-year cycle. Okay, and it's really a 22-year cycle, because the polarity switch between the north and the south every other cycle, right, which is pretty neat. Okay, and there's more than 11-year cycle, because 11 years, if you think you have a star that's been around, our sun, a star, but our sun, that's been around for, some 4.5 billion years. Well, you might imagine that there's other cycles that are less frequent than 11 Earth years, and us with our short lifespans aren't able to comprehend them. One idea is that there looks to be about a 100-year cycle where there's variation between the actual relative height of the peaks. And back in the 1600s, there was the Maunder minimum, where there was almost no sunspots recorded for many generations, right? Few generations. Okay, so the sun is very active. It's active with the rest of the solar system. What do I mean by that? Well, it's spewing out energy, and not just energy as the photons and that measured luminosity and the intensity and solar, the solar value that you have here here on Earth or other planets, but just in terms of charged particles, and there's a solar wind, in terms of big chunks of plasma just floating out into space. There's lots of activity. Okay, so the areas around the sunspots are active. Large eruptions may occur in the photosphere. A solar prominence is the most common example of that, which is a large sheet of ejected gas. So the solar prominence comes up, like a bunch of plasma starts building up on those field lines, because these would be magnetic field lines that the plasma is following. But sometimes a lot more will follow those field lines. The field lines will be particularly strong, for example. And so then all that material starts clumping up. Some of it will gradually break off, but much of it will just kind of get carried along the field lines. Now, there's something really similar, which is a solar flare, which is a bunch of plasma, and some of it getting carried along field lines. But unlike the prominences that build up over many days, they gradually build up, a solar flare is an actual explosion, and it just happens in a few seconds or minutes. All right, so it just blasts out. Right, pretty neat, and much more dramatic release of energy even than a solar prominence. And although we shouldn't downplay solar prominences, if you consider that that Earth is like something about that size right there, you can see that these solar prominences are hundreds of times bigger than Earth. They're pretty dramatic in their own right. They just take a few days to form, as compared to a solar flare that just happens almost instantaneously. Now, another thing that the sun does, which is even more dramatic, is a solar mass ejection, which is where a large bubble detaches from the sun and then floats off into space. So there's just a big mass of plasma that kind of builds up, gets its own almost form, and then has enough energy to have a gravitational escape velocity, and just kind of gets flung off of the sun and then floats off into space. It's got its own kind of like swirling magnetic field, and it can just float off and then bump into a planet. They're often many times larger than planets. So here's an example of a solar mass or coronal mass ejection coming up and then just drifting into Earth's orbit, bumping into Earth, but then getting kind of fed into Earth's magnetic field, where all the charged particles are going to get pulled down to the poles, which would create very, very dramatic aurora borealis on that particular day or a series of days. And then, but overall, the magnetic field of Earth more or less protecting us from this coronal mass ejection, because otherwise all that plasma would just hit the surface, which would be problematic for, say cell mutation and so on. But the magnetic field, helps direct it to just the poles and just absorb a lot of the energy because it gets trapped along these helical paths along the field lines. Okay. And additionally, there's the solar wind itself. The solar wind is composed of electrons, protons, and something called alpha particles, which are ionized helium. So it's helium without any electrons. So it's 2 protons and 2 neutrons. That's an alpha particle. All right. So the solar wind is composed of those, with the most common element being the electrons. And the solar wind escapes the sun mostly through coronal holes, because otherwise all those charged particles are trapped in the sun's own magnetic field. But sometimes the magnetic field lines just kind of go off and don't loop back around on themselves in any scale relative to the solar system. So instead, that allows for the solar wind to just flow out to that almost opening in the magnetic field of the sun, which is really fascinating and important, because in that solar wind is a continuous process of plasma that's getting pushed out into the rest of the solar system. It's very low density, much lower density than, say, like a big clump like a coronal mass ejection, but it's steady. And it may not always be pointing into the same part of the solar system, but it's always spewing off into some part of the solar system. For example, we could see it going off in this direction, like a hole in the corona. Because here we can see the solar corona has a very unusual shape, all right, and it has some big gaps that would allow the solar wind to flow out at this particular time, and it's always varying over a few Earth years. Okay, now does this effect of big clouds of plasma and a steady rain of ionized particles in the solar wind, does that affect Earth? Is there a solar terrestrial relationship? Yes. All right. There is a possible connection. There is understanding of what's happening, although we don't quite know why, because the energy output doesn't vary that much. So why is it affecting Earth? Why do we see changes in our data? Well, let's leave it up for further observation and further study. All right, so now on to the heart of the sun as we near the end of this discussion. Okay, so we want to talk about this amazing production of energy inside the sun. So given the sun's mass and energy production, we find that on average, every kilogram of the sun produces about 0.2 milliwatts of energy. That's not much, right? So it's not like the sun is incredibly efficient. Okay, a gerbil could do better, right? So like a metabolism in a mammal produces more energy per mass. But if it continues through the 10 billion year lifetime of the sun, so the sun is an amazing output of energy because it's so massive. So even though it's inefficient per kilogram, it's not that massive, not that much energy, but there's so much mass, so there's so much energy. And the other thing that makes the sun remarkable, which I haven't mentioned, but is highlighted right here with this lifetime idea, is that it does it for so long. Because yeah, sure, the gerbil is more efficient, but the gerbil only lives a few years. The sun can keep doing this for billions of years, billions of Earth years. And that's the thing, it's a huge amount of steady energy. All right, so we find that the total lifetime energy output of the sun is about 3 times 10 to the 13 joules per kilogram. So now there's a lot of energy, right? But it's steady, it's spread out. Okay, how does it producing energy over such a long period of time so steadily and so much of it? Well, the only explanation is nuclear fusion. That is the energy source of the sun. Scientists, physicists, astronomers conclusively know that that's how a star like our sun produces energy, through nuclear fusion. Okay? In general, nuclear fusion works like this. You have one atom plus another atom, and it becomes a larger atom. And in that process of 2 small atoms, nucleus 1 and nucleus 2, becoming some larger third nucleus, there's a release of energy. That's what fusion is all about. But why? Why would the process of smashing 2 things together produce energy? Well, it comes from mass. Because if you add up the masses of the 2 initial nuclei, the 2 small nuclei that were fused together, we find that the result is more. There's actually more mass to begin with in this initial adding together nuclei. And that mass became energy, because the final nucleus, nucleus 3, is less massive. All right? So M3 is smaller than M1 plus M2. And that missing mass got converted to energy. It got converted to energy through E equals mc squared. The idea that rest mass can become energy, one of Einstein's most famous equations. All right? The relationship between the mass and energy comes from Einstein's famous equation E equals mc squared. In this equation, c is the speed of light, all right, which is a very large number. It's 3 times 10 to the 8 meters per second. So a very notable number. What that means numerically, kind of an important idea, is that means we get a lot of energy per mass. You don't need like, you just need like, a tiny fraction of a gram to get a lot of energy. Okay, that's the idea, because c is such a big number. And you think about, you're multiplying by this big number, some 300 million, and you're squaring it. My gosh, that's a lot of energy, right? What this equation is telling us is a small amount of mass is equivalent of a large amount of energy. Tapping into the energy is how the sun keeps shining so long, right? So it is an amazing energy source. We want to tap into it if you want lots of energy. Now we tap into the energy of mass here on Earth through fission, which is what a nuclear power plant does. All right. So fission is also tapping into the same equation, E equals mc squared, but not as much. It's not as efficient. All right. So nuclear fusion, what the sun does, unlike what a nuclear power plant or a nuclear bomb does, which is fission, but the sun, getting back to fusion, requires that like charged nuclei get close enough to each other to fuse together, because they don't want to. If you take two protons, there's an electrostatic repulsion between them, and so they'll get close to each other and then push away. But if it's hot enough, they can get even closer to each other, and they're not able to push away, and instead they stick together and they become something new. In this case, the two protons become deuterium, which is a isotope of hydrogen, because now it has a proton and a neutron. See what happened? And to maintain charge, because charge cannot be created nor destroyed, there's a little positron that's created, which is the positive version of electron. And this thing won't last long because it'll get annihilated when it interacts with an electron. Okay, but lots of little details there in terms of the process. But the idea is that there is enough energy and temperature, so high temperature, that allow these two protons to smash together. Okay, that's why you need that 10 million Kelvin. You can't get fusion without 10 million Kelvin. Okay, and that's specifically fusion of protons, by the way, which are you can think of this as ionized helium. All right. And the idea is that it's the most basic building block of matter. You can fuse other things. You could fuse helium itself into something. You can fuse carbon even, but then you would need even a higher temperature. So the previous image depicts the proton-proton fusion. That's that proton-proton chain we're talking about. In this reaction, you get a proton plus a proton, which becomes deuterium, that isotope of hydrogen, plus a positron plus a neutrino. Okay. Now, neutrino was in this previous picture. It was over here. I didn't call attention to it, but we'll be talking about this. Neutrino is a weird particle. It doesn't carry charge like all these other ones, but it does carry angular momentum. It's very important to physics and very important to the study of the sun. So the positron is just like the electron except positive. The neutrino is also related to the electron. So it's the same category of particle, but it is chargeless. And again, its only purpose is to maintain angular momentum. Because it turns out that in quantum mechanics, angular momentum is quantized. Okay, and so this is representing it in more of notation form. So we have that proton, which is represented here as hydrogen, because it is ionized hydrogen. Here's another proton, and there is the deuterium, which is 2, represents the fact that it has 2 nuclei, or 2 nucleons, 2 particles in its nucleus, 1 proton, 1 neutron. There's the positron and the neutrino. Okay, here it is represented pictorially. So you can see the process, and this is why it's a chain, because that idea of producing a deuterium from 2 protons, it's just the first step, because then that deuterium combines with another individual proton to form helium-3. All right, now this is an isotope of helium rather than an isotope of hydrogen. Finally, 2 sets of helium-3, which each came from their own chains, see? Then they fuse together in one final fusion to form helium-4, the final product. So what's happening then is all those protons, all the hydrogen, because a proton is hydrogen, right, just by another name, all that hydrogen in the sun is becoming helium-4, which is the most common stable isotope of helium, basically basic helium. Okay? So the second step is the formation of an isotope of helium. We already talked about that. That's the helium-3. The final step takes 2 of those helium-3 and forms the final product, the helium-4. And an extra 2 protons, which then will continue on to start the process anew. So it's a continual chain reaction. All right, so here's the ultimate result. What comes in, 4 protons was the original ingredients. You can see that here, because if you look at all the original starting points, it's just 4. There's the other one there. All right, here I'll put boxes around them. All right, so here are the original 4, where's the last one? that one came in. Oh, there it is. Okay, so this is the original 4 inputs. See the 4 boxes, that's what came in was 4 protons, and the final output is just a single helium and 2 little leftovers. Okay, and what else? Well, you also have the extra neutrinos, don't you? All right. All right. And the helium stays in the core for now. Eventually, as our sun gets really old and starts to expand out because it will be actually heating up more and gravity won't be able to hold it together anymore, well, then it will start finally fusing that helium into other things like carbon. All right. But that's at that point that we won't be living on Earth, and it's in a few billion years from now because the sun will actually consume Earth. The energy in this form, the energy is in the form of gamma rays. That's the extra energy that's created. All right. It's also going to be in the form of the kinetic energies of the particles. So the kinetic energy of the hydrogen that's produced, or of the helium, and the extra hydrogen is also going to be where this energy goes. But some of it does go into pure gamma rays. All right, and those gamma rays gradually lose their energy as they travel out from the core. Right, so they're going to mostly lose their energy, those gamma rays, when they get absorbed into the convection layer. So they'll transmit through the radiation level, they'll get, which is transparent, but then they'll hit the opaque convection level. That's where they get absorbed and then re-emitted as visible light at the photosphere. So it's not the same photon, but it's the same energy. And the neutrinos just escape right out. How is that possible? Well, neutrinos basically don't interact with matter. They're very unusual particles, so they're going to pass through almost never interacting with matter. But they do make their way to Earth, but if they don't interact with matter, how do we detect them? Well, they interact with matter very, very weakly, so we use some ingenious detection techniques, which I'll talk about in just a moment. But let's summarize or finish up talking about the heart of the sun. So the energy created in the whole reaction can be calculated by the difference in mass between the initial particles and the final ones. For each interaction, it turns out that you have 4.3 times 10 to the negative 12 joules, so small amount of energy per interaction, of course. And then this translates to 6.4 times 10 to the 14 joules per kilogram of hydrogen. Right? So that's actually how much energy you're getting per kilogram. So the sun then must convert 4.3 million tons of matter into energy every second. And I talked about this in the very intro to the lecture. I said there's a lot of matter becoming energy in the sun. That's amazing. That means the sun is becoming 4.3 million tons lighter every second. Wow, that's a lot of matter just disappearing. Does that mean the sun is shrinking rapidly? Well, no, the sun has so much mass that 4.3 million tons is a drop in the bucket. It's a drop in the ocean. Right? It hardly matters. That's why the sun is going to continue to live for about another 4 billion years. Right? So the sun has enough hydrogen left to continue fusion for another 5 billion years. Right? 4 to 5. Okay? So the fundamental forces, by the way, because we're talking about this idea of fusion, are gravity, which is very weak but can continue to grow, right? So it's infinite in range. Electromagnetic, okay, that's the force that wants to repel light charges, which is much stronger, but can be repulsive, as we know. It can also be attractive when you have like an electron and a proton holding a stable, cool atom together. Then there's the weak nuclear force. This is responsible for beta decay, which is basically where electrons are produced from unstable large nuclei. And it's a short range, basically only about 1 or 2 protons in diameter, very, very weak. Then there's the strongest force in the universe, which is the nuclear force. And by the way, the weak nuclear force, not super relevant to fusion, so don't worry about it too much. But the strong nuclear force, very relevant to fusion, because it's what keeps the nucleus together. It explains that difference in energy, why there's more energy per nucleon in a proton than there is energy per nucleon in helium. Why that there is that loss of mass? Because what is the mass? The mass is the binding energy of the matter in the nucleus itself. All right, and in the sense it's called the strong force for a reason. It's by far the strongest force in the universe. That's why there's so much energy in rest mass. That's why E equals mc squared works. All right, and this idea of the fundamental forces actually came after Einstein. It was sort of a refinement of Einstein's famous theory. All right. And the energy generation in the proton-proton chain, well, we can look at the numbers. So thinking about the strong nuclear force, the mass of 4 protons is this much, basically 6.6947 times 10 to the negative 27. Right? That's going to be your order for things like this, kilograms. The mass of the helium is this much, right? Well, notice, right, there was a loss, right? The 9 became a 4. There's a loss of mass. So the helium, even though it was formed from those 4 protons, it's lighter. So the mass transferred to energy is this much. all right? So about 0.71%. So not a lot, right? A tiny fraction, right? Most of it remained as the binding energy, as the strong nuclear force of the nucleons themselves, or them, holding the nucleons together. But some of it just disappeared, all right? And so that small loss of mass is equivalent to this much energy by E equals mc squared, all right? And so then the energy produced by fusion of 1 kilogram is this much, as we talked about before. All right, so now finally on the neutrinos, those weird particles that are produced in this proton-proton chain, fusion chain, well, that apparently don't interact with matter very well. What happens? Well, they're emitted directly from the core of the sun, and then they escape because they hardly interact with everything in there. They don't bump into electrons, they don't bump into protons, they just kind of scoot right by them, okay? So they interact with virtually nothing. Being able to observe these neutrinos would give us a direct picture of what is happening in the core, since they just travel straight out nearly the speed of light. It only takes them about 8 minutes to get to Earth. None of that 1 million year delay, all right? Unfortunately, they are no more likely to interact with Earth than they are with the sun, right? The only way to spot them is to have huge detector volume and be able to observe a single interaction event. So we build these giant tanks of particular fluids, and we build them deep underground, so there's no noise in our signal. Usually abandoned salt mines. Scientists will spend millions of dollars building these neutrino detectors, and they only detect like the tiniest signal from them. And really, I mean, these are huge investments to build these neutrino detectors. But if you think about it, it's not a waste of money because it's our only way to know for sure what's happening with the sun that sustains life as we know it. Okay, this is what a neutrino detector looks like, right? Quite science fiction. They build them deep underground in these abandoned mines or just decommissioned mines. Excuse me. Right? You can see that the huge tanks of water. This would be inside here is the tank, and here's someone actually working on the tank before it's full. And they usually fill it with a very filtered water or other mixtures of fluids. All right. And they don't work all that well, but they work just enough to detect a few neutrinos. And the detection of solar neutrinos has been an ongoing study over the last 50 years, and it's more closer to 50. And there's always been a deficit in the type of neutrinos expected. For a long time, scientists didn't know why. Eventually, they figured it out, and a Nobel Prize was awarded to the team of scientists that did figure it out. And the recent discovery, they found out that the neutrinos are actually changing as they travel from the sun to the earth in those 8 minutes, which is really important because it let us understand a lot about relativity and about the very nature of these incredibly light particles like neutrinos, which we had thought for a while actually might be massless, but they're not because they change, which means that they have to have mass because they have a time-dependent behavior, which is one of the ideas of special relativity, Einstein's theory, which is actually the same theory that leads to E equals mc squared. Okay, so let's finally summarize. Right? And by the way, neutrinos are important because they give us a window into the sun, special relativity aside. But let's summarize chapter 16 and wrap this up. So the main interior regions of the sun are the core, the radiation zone, the convection zone, the photosphere, the chromosphere, transition region, corona, and the solar wind. Solar wind is what outputs in the rest of the solar system. And the solar wind spreads all the way out to the very edge of the solar system, by the way. Energy comes from nuclear fusion, all right, which produces neutrinos, all right, and a lot of energy. The standard solar model is based on the hydrostatic equilibrium of the sun. So gravity pushing in, fusion pressure pushing back out. That's what the hydrostatic means, okay? The study of solar oscillations leads to information about the interior because other than neutrinos, looking at the oscillations is our best way of knowing for sure, that our models are correct. The absorption lines in the spectrum tell us about the temperature and the atmosphere. And it's important because the elements that exist in the atmosphere, that exotic atmosphere with those heavy elements, well, that's good because it tells us, because those elements can only exist if the sun is sort of burning at a certain temperature. So that definitely gives us a window into it. Sunspots, we know, are associated with magnetism, so are a lot of those solar prominences and other phenomenon. And they have an 11-year cycle, right? 11 Earth years. Large solar ejections, prominences, flares, coronal ejections, all that stuff is just fascinating and really dramatic. And the neutrinos show a deficit due to the peculiar neutrino behavior, which is a window into particle physics itself. All right, well, I hope this rather long lecture on the sun has been both interesting and informative. Thank you so much for watching.